Hello everyone, my name is Sharath Kumar. I am going to discuss with you the topic on error detection and correction, which is the very important topic in computer networks. Error detection and correction. Why this is important? Because see, data can be corrupted during the transmission. Some applications require that errors should be detected as well as corrected. Introducing the topics, what we are going to discuss is the types of errors, redundancy, detection versus correction, forward error correction versus retransmission, coding, and modular arithmetic. In the first topic, we discuss the types of errors. We have two types of errors, that is a single bit error where only one bit in the data unit has been changed. As you can see in the diagram, the 0 bit is being changed to 1. The second type of error is burst error. Here it means that two or more bits in the data unit have been changed. As you can see in this, 4 bits have been changed from 0 to 1, or it may be from 1 to 0. But for our example, we are considering a length of burst errors as 8 bits. So to detect or to correct errors, we need some extra bits with the data. That extra bits are known as the redundant bits. As you can see, this is the typical structure of an encoder and the decoder. Encoder here is the sender and the decoder is the receiver. Encoder will first generate the message by the help of a generator to get a message as well as the redundancy bit. This message and the redundancy bit will be transmitted to the receiver via unreliable transmission medium, and the receiver is going to receive that information and is going to check whether any error is being generated by that message. If it is correct, it is being accepted. If it is an error message, it will be discarded. Then in modulo arithmetic, we use only the integers in the range from 0 to n-1 inclusively. And you can see here we are XORing a two single bits or a two words. So if the bits are same, the result will be 0, and the bits are different, the result will be 1. The next topic is block coding. In block coding, we divide our message into blocks of each of k bits called data words. We add r redundant bits to each block to make the length as n equal to k plus r, where n bit blocks are called the code words. And the topics to be discussed under block coding will be error detection, error correction, Hamming distance, minimum Hamming distance. So first of all, the data words and the code words in the block coding are being divided into k bits. The data words are k bits. 2 power k data words each is having k bits. N bits where 2 power n code words each is having of n bits. And you can see the process of error detection in block coding. The same thing, each k bits of data word will be sent to a generator where it is going to generate n bit of code word which is involving the redundancy bit. Via unreliable transmission, that code word will be transmitted to the receiver, and then further it will be checked by a checker. So if the checker is giving the correct message, then the data word will be accepted. Else that is considered as error and it will be discarded. So if you take for example k equal to 2 and n equal to 3, assuming the sender encodes the data word as 01 as 011 and sends it to the receiver is going to receive 011. It's a valid code word. The receiver extracts the data word 0 from 1 from it. So the code word will be, if it is corrupted during the transmission and if it is receiving 111, this is not considered as a valid code word, it will be discarded. The third case is the code word is corrupted during the transmission and it is receiving 000 is received. This is a valid code word. The receiver incorrectly extracts the data word 00. So two corrupted bits have made that error can be undetectable. So in block coding, only single bit error can be detectable. And these are the code for error detection. Suppose the data word is 00, you are going to get the code word as 000. Then the error detection method can detect only the types of errors for which it is designed. Other types of errors, it may remain undetected. So the structure of error detection, that is error correction using encoder and decoder, is shown in this figure. So you can see the sender and the receiver, which is acting as similarly as encoder and the decoder. Here the k bits of data word will be sent via generator to form a n bit of code word. Via unreliable transmission, the code word will be received and it is going to check by the checker, and it will be correcting the error and the data word will be accepted. So this is the examples for each of that error correction. So we'll further move on to the Hamming distance. So Hamming distance, it is between the two words, is this number of differences between the corresponding bits. So if you want to find out the Hamming distance between the two pairs of words, for example D of 000 and 011, it will be 2. You take an exclusive OR of 000 and 011, how many number of ones is the remaining in the result will be giving me the Hamming distance. Next, the minimum Hamming distance is the smallest Hamming distance between all possible pairs in a set of words. So if you take the Hamming distance of the following code, so suppose D of 000011, it will be 2, and all the other case it is 2, so the minimum Hamming distance will be 2. So second case is, if you want to find out all the Hamming distance, among them we get 3 and 4 as the Hamming distance. Among them the minimum Hamming distance will be 3. So to guarantee the detection of up to S errors in all the cases, the minimum Hamming distance in block code should be S plus 1. So if you find the minimum Hamming distance for our first code scheme, it is 2. So the code will guarantee the detection of only a single error. For example, if the third code word, suppose 101 is sent and one error occurs, the received code word does not match any valid code word. If two errors occur, however, the receiver code word may match a valid code word and errors will be not detected. So like this, the things goes on for the block coding. So these are some geometric concepts for the finding the D mean in the error detection and correction. And one more important point is, to guarantee the correction of up to T errors in all cases, the minimum Hamming distance in a block code must be D mean, which is 2T plus 1. So you can see here the code guarantees the detection of up to 3 errors if S is equal to 3, but it can corrupt up to 1 error. In other words, if this code is used for error correction, part of this capability will be wasted. So error correction codes need to have an odd minimum distance. So the next concept is linear block code.